So we saw before that given any complicated network, it is possible to simplify them and write them as either a Thevenin equivalent circuit or as a Norton equivalent circuit. So if it is a Thevenin equivalent circuit, it consists of a Thevenin voltage and then a Thevenin resistance in series with it. So this is Thevenin equivalent circuit. Or you can also write the Norton equivalent circuit, which consists of a constant current source, IN, Norton current, and this is in parallel with the Norton resistance. And the question that now we want to ask is, what is the relation between these two equivalent circuits? And the answer to this is very straightforward. So you want to relate IN and RN with VTH and RTH. And the relation between these is VTH is equal to INRN and RTH is RN. RTH equals to RN is something that should be obvious because the method of calculating them was exactly the same. But the relation between the voltage and the current in the two cases is given in this form. One question that you might have is, when should I use Thevenin's theorem and when should I use Norton's theorem? There is no fixed answer for that. For certain problems, depending on the kind of complicated network that you're analyzing, in some cases it might be more useful to use a Thevenin equivalent circuit. In some cases it might be more useful to use a Norton equivalent circuit. So this is something that I cannot give a general answer to. It's something that will depend on a case-to-case basis. And as you do more and more problems, and you do more advanced electronics, it might become easier for you to gauge which of these two methods is better to use. Okay, so this was a discussion about Thevenin's and Norton's theorem. Now we're going to move on to the next network theorem that we are interested in, and this is called the superposition theorem. Superposition theorem is useful when you are looking at circuit networks in which there is more than one source. So you can have multiple voltage sources, you can have multiple current sources, or you can have some voltage sources, some current sources. So let's just take one example just to see. Suppose I have a circuit that looks like this. So here, this is a voltage source. Then let's put some resistances. Let's call this R1, R2, R3, and over here I'm going to put a current source. And now suppose I'm interested in finding out what is the current that flows through this resistance R3. Now there are two sources. Superposition theorem says that each of these sources acts independently, and you can calculate the current independently for each source and then just add them up. You will get the total current. So first, let's only consider the voltage source. So when we do that, we will replace the current source by its internal resistance, which in this case is infinity. So then the circuit will look like this. and nothing over here, because this has been replaced by an infinite resistance. So it's as if this circuit has remained open over here. So when you do this, obviously there will not be any current flowing through R2. Whatever current flows this way will then flow here. And then let's say the current over here is, let's call it, what should we call it? Let's call it I31. And then in step 2, I'm going to ignore this voltage source and I'm only going to consider the current source. So we'll replace the voltage source by its internal resistance, which is 0. So now the circuit will look like this. Now the current from here, current I flows this way, some of it flows through this branch, some of it flows through this branch, and then it combines and comes this way again. So now let's call the current in this branch as I32. And then what superposition principle tells us is that I3, which we wanted to calculate, is simply I31 plus I3. So the current in any branch of the circuit is just a sum total of the different sources taken one at a time. That is the superposition theorem. It's a very straightforward theorem, nothing much to describe over here as such. In fact, why don't we do this explicitly? So if you look at this diagram 1 over here, there is no current flowing through R2, so the entire current flows through R1 and then R3 in series. So I31 is just E divided by R1 plus R3. And if you want to calculate I32, now this becomes a little complicated. So the current I, which is flowing through this circuit over here, it splits because of these two resistances R1 and R3. So I32 is just going to be this I, and then because this gets divided, R3 divided by R1 plus R3. No, this should be R1 divided by R1 plus R3. And so I3 is just E plus IR1 divided by R1 plus R3. So this is the superposition theorem for you. The next theorem that we are looking at is what is called the reciprocity theorem. This is a very interesting theorem. Let's again look at it in the context of some example circuit. So here is a voltage source E, and suppose because of this voltage source E, there is a current I flowing through this resistance R3. What reciprocity theorem says is that suppose if I was to interchange E and I, then the current would still be the same. So basically, instead of putting the voltage source over here, if I put the voltage source over here, then the current in this branch would be exactly the same current I. So if a voltage source in branch 1 generates, if a voltage source E in branch 1 generates current I in branch 2, then the same voltage source E in branch 2 will generate the same current I in branch 1. So if I were to make a circuit that looked like this, so I'm going to put the voltage source where I was measuring the current before. Then the current flowing through this branch over here will be I. So this is the reciprocity theorem. It's fairly straightforward. And then the last next network theorem that we are interested in looking at, and this is a pretty useful one, is called the maximum power transfer theorem. Now, when you're building more and more complicated circuits, often the circuit is built in different stages. So for example, you might have one complicated network over here, which is stage 1 of your circuit. And from stage 1, you get some output. And then this output of stage 1 goes as the input to the next stage. So call it stage 2. Then you're going to connect these two. So output of one stage goes and becomes the input of the next stage, and so on and so forth. So now, of course, every stage will have some effective resistance. So this has some effective resistance over here, which let's call it the output resistance of stage 1. And similarly, this stage 2 will also have some effective resistance between these terminals. Let us call this the input terminal of stage 2. Now what the maximum power transfer theorem says is that the transfer of power between these two stages, stage 1 and stage 2, is most efficient when the output resistance of stage 1 is exactly equal to the input resistance of stage 2. So if you want to optimize the power transfer, then the output resistance of the first stage must be equal to the input resistance of the next stage. This is the power transfer, maximum power transfer theorem. And this can actually be proved using Thevenin's theorem. So let's quickly look at the proof. So stage 1 is some complicated circuit. We can write it effectively using Thevenin's theorem in terms of some V Thevenin and some R Thevenin. And this R Thevenin is exactly this effective output resistance, R out 1. And this I'm going to connect to the input resistance of R2, which in this case is playing the role of the load resistance. So now it's easy to calculate what is the current flowing through the load resistance. It is just VTH divided by RTH, which means that the power is I square R. So power is going to be IL square times RL, which is VTH square RL divided by uh, this is RTH plus RL because we have connected the load in series with the Thevenin resistance. So this is RTH plus RL the whole square. Now if you want to maximize the power transfer with respect to, let's say, RL, then I'm going to do dP by dRL equal to 0 and find the condition for it. And you can calculate from this what the condition will be. That will turn out RTH has to be equal to RL in order to maximize the power being transferred. And this is the same as saying that the output resistance of stage 1 has to be equal to the input resistance of stage 2. So this proves the maximum power transfer theorem. So in this chapter or in this module, we have looked at 5 theorems: Thevenin's theorem, Norton's theorem, superposition theorem, reciprocity theorem, and the maximum power transfer theorem. And we will use these theorems in doing some of the analyses that we are going to be doing throughout the rest of this course.